Assignment 2. Visual Learning in Science Research and Application to Your Classroom. Review of an article related to this topic was done by me for Chem 6750 for Dr. Cortes' class. The article that I reviewed was Promoting Conceptual Understanding of Chemical Representations, Students' Use of a Visualization Tool in the Classroom. This research was done by professors at University of Michigan. Primary goal of this research was to determine if computer models can be used effectively for 11th grade high school students who have never learned organic chemistry before. Also, look at how these students develop their understanding of chemical representations and what features of the technological tool supports them to do so. Most of the models that were available previously were used by professional chemists and college students. None were for high school students. Students using the technological tool eChem for this research developed schema to visualize chemicals. For high school students, making connections between chemical representations and concept is not automatic as it is for a chemist. In our readings this week in Chem 6750, we have learned how students do not understand chemical representations such as bond lines, arrows, dots, chemical codes, subscripts, coefficients, and superscripts. If you remember, Hoffman pointed out in his research, chemistry is a language in itself. Chemists can represent atoms as everyday objects with a reasonable size and can envision molecules colliding and electrons moving. Chemical structures, chemical formulas are the signing tools, and the idea is to use these accurately to relate the connectivity of atoms and spatial relationship with their neighboring atom. As a professional chemist, we do understand these concepts, but imagine a non-chemist being introduced to these concepts. This non-chemist learning chemical representation is the focus of this article. Earlier researchers had explored these concepts and narrowed that students have trouble visualizing, following chemical concepts and relating to chemical processes at particulate level, symbolic level. Students had trouble translating chemical concept and had trouble understanding. For example, when they see a chemical equation, they do not see bond formation and bond breaking. All they see is letters, symbols, and arrows. Earlier research has shown that being able to manipulate physical models and computational models offered long-term effect on students' understanding. There had been a lot of technological models or tools available in the marketplace. Multimedia and mental models, Tinker, RASMol, MathMol. But most of these were for college students and for professionals. None of them really focused on high school students. The idea behind using technological tool is that when students understand representations, they should be able to generate interpretations, make translations, and mentally manipulate these representations. None of these tools focused on novice high school students, did not analyze how students developed understanding of chemical representations over time. Students were not able to change the representation to meet their learning culture. As we go through this review, please keep Pavio's dual code theory in mind. Pavio's theory stated that visual and verbal information are processed differently and along distinct channels in the human mind. The theory assumes that there are two cognitive subsystems, one specialized for the representation and processing of nonverbal objects, and the other specialized for dealing with language. Take a look at this theory and keep it in mind as we go through once again. This research shows that visualization is a process involving the conceptual verbal and visual nonverbal connections within individual cognition, just as Pavio's dual theory does. The essential questions that the researchers tried to answer with this study were: what does a technological tool like eChem help students translate 2D and 3D visual representations? What patterns do students demonstrate while translating? What conceptual understanding do these patterns reveal? The tool eChem was integrated in a 6-week toxin project where the 71 high school students involved in this research were educated on chemical concepts. They watched videos of water treatment, environmental science videos, built physical and eChem models, and designed web pages for final products. Week 2 to 4, students performed activities to capture the goal of eChem. The first eChem activity was tied to a lecture on covalent bonds and structures and properties of organic compounds. Students constructed models of alkanes, viewed various representations simultaneously, and developed an understanding of the relationship between boiling points of alkanes and their number of carbon atoms. The second activity introduced the IUPAC nomenclature of organic compounds. Students created models on eChem and followed the rules to name their models. The eChem 3 activity was designed for students to visualize 2D and 3D models of chemicals. The 2D representations included structural formulas, condensed structure formulas, and chemical formulas. The 3D models constructed in this activity were ball and stick, space fill, and wireframe models. Let's take a look at the technological tool that was used in this research, eChem. A technological tool should meet the needs of the learner, help in acquiring knowledge and concept, provides growth in subject matter, addresses diversity of learner, and sustain motivation. And eChem geared towards all of these requirements. Basically, eChem can be split into 3 tasks. Construct. Students can create organic molecular models, view them from all possible angles, and manipulate them. Visualize allowed students to have multiple views of different compounds and various representations, such as ball and stick, wireframe, and space filling simultaneously. In Analyze, students can make connections between molecular models at the microscopic level and their collective behaviors at the macroscopic level. Example, chemical and physical properties. This is an interface picture of the Construct and Analyze framework of the eChem models. In Construct, students can create organic molecule models, view them from all possible angles, and manipulate them more easily than physical ball and stick models. In Analyze, students can make connections between molecular models at the microscopic levels and their connective behaviors at the macroscopic level. Notice the color and graphics in these visuals. Research has shown that these enhance students' learning. eChem also allows students to create their own database of compounds over time. Data was collected over a 6-week period. Curriculum materials were used, classroom videos, video recording of students using eChem, field notes, interviews. Participants were given a pre-test and a post-test where questions geared towards chemical representations, chemical concepts, underlying representations, information about molecular structures and properties connections. Above all, the target students were also given similar type of things. They were also given an interview where they were asked to predict a chemical compound's polarity and solubility, provide explanation, represent organic compounds various ways, make translation between various representation, and visualize. Data was categorized into 3 categories: process video, process interviews, and artifacts. Process videos provided details on how target students use this tool and were coded by analysis scheme, which involved students' interactions with teachers and researchers and actions of using eChem. In essence, the frequency or how much time did they spend on a certain feature in eChem. For example, model rotations and chemical formulas. Process interviews basically involved to access target students' understanding of representation, properties and structures, translate, and concepts. Artifacts, this included worksheets of eChem activities and models built by eChem. Curriculum materials, classroom videos, and field notes of classroom observations. They were collected to describe the implementation of curriculum. Four themes emerged basically from this research that were related to students' engagement, how much the students, how much time they spend with the EChem. The theme number 2 depended on the physical and computation model that served as thinking vehicle for the students. Theme number 3 involved the process of visualizing. And theme number 4 involved if all of these 3D models were useful or not. Students' engagement was correlated to their conceptual understanding. When students were highly engaged in constructing, visualizing, and or analyzing molecular models, their discussions involved the conceptual aspect of representations through which students made these representations meaningful. Theme 2. Both physical and computation models served as a thinking vehicle for students to manipulate mentally. Student perceptions of EChem and 3D models were explored in this theme. Basically, how the students formed and were they able to manipulate a model mentally, like using EChem to rotate the 3D models. Did they like working with physical model as well? And here's an example of a student discussing with his teacher, Mark, about and looking at the isomers. Basically, physical and computation models were carrier of students' mental images. Students also noticed the limitations and advantages these two types of models provided. Now, this is where I really want you to bring up Pavio's dual code theory in your mind. Let's take a look at this theme. The process of visualization involved retrieving relevant information and activating verbal and nonverbal connections in individual cognition. You will notice here a transcript between two students, Brian and Richard, and how they determine the structure of cyclopentane would be. They did not know it was cyclopentane. They were just given the formula C5H10, and they themselves formulated the explanation that alkanes need to be 2n plus 2. They were not told that by the teacher. Okay, so, and here you can see how Pavio's theory plays a role. Keep in mind that making translations between chemical representations could involve not only retrieving conceptual knowledge of chemical representations, but also creating mental images of them. Theme 4 showed us some of the models that students did not really care for. For example, they chose a ball and stick model over the space film model, even though it was visually very attractive to them. Same was the case with wireframe model. Since they could not see the atoms, it was just too abstract for them. They could only see the carbon chain. Students explored different features in EChem. Basically, the rotation feature in EChem helps students visualize how to transform a 2D model into a 3D model. The feature also assisted students in constructing models. The chemical formula displayed on the construct page assisted students in identifying empty bonding sites and translating a structural formula into a 3D model, as they frequently compared the chemical formulas in EChem to the ones they intended to build. This study focuses on connectivity between traditional learning in conjunction to models. A positive learning effect shown by the significant difference between the scores of pre-test and post-test may be partially attributed to using a visualization tool in science classrooms. A computer-based visualization tool like EChem in particular improves students' ability to make transformations between 2D and 3D models, and this ability might help them to develop an understanding of isomers and polarity. This study does not conclude that either the computation model or the concrete model is the best for chemistry learning. Instead, through analysis of interviews and process videos, this study suggests that both types of models should be provided through class instructions, because different students have preferences for different types of models and symbol systems. Following are the takeaways from this research. Technological tools such as EChem extend students' understanding of atoms, chemical bonds, and molecules. Teachers could take basic understanding of chemical bonds and guide group discussions of how different models convey different information of bonding, atom, size, and electron. This study reveals that constructing visual connections between representations is as important as making conceptual connections for chemistry learning. This is a list of references I use. Thanks.